Spin, physics. Spin is a conserved quantity carried by elementary particles, and thus by composite particles, hadrons, and atomic nuclei. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum of orbital revolution and appears when there is periodic structure to its wave function as the angle varies. For photons, spin is the quantum mechanical counterpart of the polarization of light. For electrons, the spin has no classical counterpart. The existence of electron spin angular momentum is inferred from experiments, such as the Stern-Gerlach experiment, in which silver atoms were observed to possess two possible discrete angular momenta despite having no orbital angular momentum. The existence of the electron spin can also be inferred theoretically from the spin statistics theorem and from the Pauli Exclusion Principle, and vice versa. Given the particular spin of the electron, one may derive the Pauli Exclusion Principle. Spin is described mathematically as a vector for some particles such as photons, and as spinors and bispinors for other particles such as electrons. Spinors and bispinors behave similarly to vectors. They have definite magnitudes and change under rotations, however, they use an unconventional direction. All elementary particles of a given kind have the same magnitude of spin angular momentum, though its direction may change. These are indicated by assigning the particle a spin quantum number. The SI unit of spin is the same as classical angular momentum, i.e., nms, js, or kgm2s-1. In practice, spin is given as a dimensionless spin quantum number by dividing the spin angular momentum by the reduced Planck constant h, which has the same dimensions as angular momentum, although this is not the full computation of this value. Very often, the spin quantum number is simply called spin. The fact that it is a quantum number is implicit. History. Wolfgang Pauli in 1924 was the first to propose a doubling of the number of available electron states due to a two-valued non-classical hidden rotation. In 1925, George Uhlenbeck and Samuel Goudsmit at Leiden University suggested the simple physical interpretation of a particle spinning around its own axis, in the spirit of the old quantum theory of Bohr and Sommerfeld. Ralph Kronig anticipated the Uhlenbeck-Goudsmit model in discussion with Hendrik Kramers several months earlier in Copenhagen, but did not publish. The mathematical theory was worked out in depth by Pauli in 1927. When Paul Dirac derived his relativistic quantum mechanics in 1928, electron spin was an essential part of it. Quantum number. Main article. Spin quantum number. As the name suggests, spin was originally conceived as the rotation of a particle around some axis. While the question of whether elementary particles actually rotate is ambiguous, as they appear point-like, this picture is correct insofar as spin obeys the same mathematical laws as quantized angular momenta do. In particular, spin implies that the particle's phase changes with angle. On the other hand, spin has some peculiar properties that distinguish it from orbital angular momenta. Spin quantum numbers may take half-integer values. Although the direction of its spin can be changed, an elementary particle cannot be made to spin faster or slower. The spin of a charged particle is associated with a magnetic dipole moment with a g-factor differing from 1. This could occur classically only if the internal charge of the particle were distributed differently from its mass. The conventional definition of the spin quantum number is S equals n/2, where n can be any non-negative integer. Hence the allowed values of S are 0, 1/2, 1, 3/2, 2, etc. The value of S for an elementary particle depends only on the type of particle and cannot be altered in any known way, in contrast to the spin direction described below. The spin angular momentum S of any physical system is quantized. The allowed values of S Arius, the reduced Planck constant. In contrast, orbital angular momentum can only take on integer values of S, i.e., even-numbered values of n. Fermions and bosons. Those particles with half-integer spins, such as 1/2, 3/2, 5/2, are known as fermions, while those particles with integer spins, such as 0, 1, 2, are known as bosons. The two families of particles obey different rules and broadly have different roles in the world around us. A key distinction between the two families is that fermions obey the Pauli Exclusion Principle, that is, there cannot be two identical fermions simultaneously having the same quantum numbers, meaning, roughly, having the same position, velocity, and spin direction. Fermions obey the rules of Fermi-Dirac statistics. In contrast, bosons obey the rules of Bose-Einstein statistics and have no such restriction, so they may bunch together in identical states. Also, composite particles can have spins different from their component particles. For example, a helium-4 atom in the ground state has spin 0 and behaves like a boson, even though the quarks and electrons which make it up are all fermions. This has some profound consequences. Quarks and leptons, including electrons and neutrinos, which make up what is classically known as matter, are all fermions with spin 1/2. The common idea that matter takes up space actually comes from the Pauli Exclusion Principle acting on these particles to prevent the fermions from being in the same quantum state. Further compaction would require electrons to occupy the same energy states, and therefore a kind of pressure, sometimes known as degeneracy pressure of electrons, acts to resist the fermions being overly close. Elementary fermions with other spins, 3/2, 5/2, etc., are not known to exist. Elementary particles which are thought of as carrying forces are all bosons with spin 1. They include the photon, which carries the electromagnetic force, the gluon, strong force, and the W and Z bosons, weak force. The ability of bosons to occupy the same quantum state is used in the laser, which aligns many photons having the same quantum number, the same direction and frequency, superfluid liquid helium resulting from helium-4 atoms being bosons, and superconductivity, where pairs of electrons, which individually are fermions, act as single composite bosons. Elementary bosons with other spins, 0, 2, 3, etc., were not historically known to exist, although they have received considerable theoretical treatment and are well established within their respective mainstream theories. In particular, theoreticians have proposed the graviton, predicted to exist by some quantum gravity theories, with spin 2, and the Higgs boson, explaining electroweak symmetry breaking, with spin 0. Since 2013, the Higgs boson with spin 0 has been considered proven to exist. It is the first scalar elementary particle, spin 0, known to exist in nature. Atomic nuclei have nuclear spin which may be either half-integer or integer, so that the nuclei may be either fermions or bosons. Spin statistics theorem main article, spin statistics theorem. The spin statistics theorem splits particles into two groups, bosons and fermions, where bosons obey Bose-Einstein statistics and fermions obey Fermi-Dirac statistics, and therefore the Pauli Exclusion Principle. Specifically, the theory states that particles with an integer spin are bosons, while all other particles have half-integer spins and are fermions. As an example, electrons have half-integer spin and are fermions that obey the Pauli Exclusion Principle, while photons have integer spin and do not. The theorem relies on both quantum mechanics and the theory of special relativity, and this connection between spin and statistics has been called one of the most important applications of the special relativity theory. Relation to classical rotation. Since elementary particles are point-like, self-rotation is not well defined for them. However, spin implies that the phase of the particle depends on the angle as, for rotation of angle theta around the axis parallel to the spin s. This is equivalent to the quantum mechanical interpretation of momentum as phase dependence in the position, and of orbital angular momentum as phase dependence in the angular position. Photon spin is the quantum mechanical description of light polarization, where spin +1 and spin -1 represent two opposite directions of circular polarization. Thus, light of the defined circular polarization consists of photons with the same spin, either all +1 or all -1. Spin represents polarization for other vector bosons as well. For fermions, the picture is less clear. Angular velocity is equal by Ehrenfest theorem to the derivative of the Hamiltonian to its conjugate momentum, which is the total angular momentum operator J equals L plus S. Therefore, if the Hamiltonian H is dependent upon the spin s, dh/ds is non-zero, and the spin causes angular velocity, and hence actual rotation, i.e. a change in the phase angle relation over time. However, whether this holds for free electron is ambiguous, since for an electron, S2 is constant, and therefore it is a matter of interpretation whether the Hamiltonian includes such a term. Nevertheless, spin appears in the Dirac equation, and thus the relativistic Hamiltonian of the electron, treated as a Dirac field, can be interpreted as including a dependence in the spin s. Under this interpretation, free electrons also self-rotate, with the Zitterbewegung effect understood as this rotation. Magnetic moments. Spin magnetic moment schematic diagram depicting the spin of the neutron as the black arrow and magnetic field lines associated with the neutron magnetic moment. The neutron has a negative magnetic moment. While the spin of the neutron is upward in this diagram, the magnetic field lines at the center of the dipole are downward. Particles with spin can possess a magnetic dipole moment, just like a rotating electrically charged body in classical electrodynamics. These magnetic moments can be experimentally observed in several ways, e.g. by the deflection of particles by inhomogeneous magnetic fields in a Stern-Gerlach experiment, or by measuring the magnetic fields generated by the particles themselves. The intrinsic magnetic moment μ of a spin 1/2 particle with charge q, mass m, and spin angular momentum s, is where the dimensionless quantity gs is called the spin g factor. For exclusively orbital rotations it would be 1, assuming that the mass and the charge occupy spheres of equal radius. The electron, being a charged elementary particle, possesses a non-zero magnetic moment. One of the triumphs of the theory of quantum electrodynamics is its accurate prediction of the electron g factor, which has been experimentally determined to have the value -2.00231930436256, 35. With the digits in parentheses denoting measurement uncertainty in the last two digits at 1 standard deviation. The value of 2 arises from the Dirac equation, a fundamental equation connecting the electron's spin with its electromagnetic properties, and the correction of 0.0023193043 arises from the electron's interaction with the surrounding electromagnetic field, including its own field. Composite particles also possess magnetic moments associated with their spin. In particular, the neutron possesses a non-zero magnetic moment despite being electrically neutral. This fact was an early indication that the neutron is not an elementary particle. In fact, it is made up of quarks, which are electrically charged particles. The magnetic moment of the neutron comes from the spins of the individual quarks and their orbital motions. Neutrinos are both elementary and electrically neutral. The minimally extended standard model that takes into account non-zero neutrino masses predicts neutrino magnetic moments of, where the μ are the neutrino magnetic moments, m are the neutrino masses, and μb is the Bohr magneton. New physics above the electroweak scale could, however, lead to significantly higher neutrino magnetic moments. It can be shown in a model-independent way that neutrino magnetic moments larger than about 10⁻14 μb are unnatural because they would also lead to large radiative contributions to the neutrino mass. Since the neutrino masses are known to be at most about 1 eV, the large radiative corrections would then have to be fine-tuned to cancel each other, to a large degree, and leave the neutrino mass small. The measurement of neutrino magnetic moments is an active area of research. Experimental results have put the neutrino magnetic moment at less than 1.2 times 10⁻10 times the electron's magnetic moment. On the other hand, elementary particles with spin but without electric charge, such as a photon or a Z boson, do not have a magnetic moment. Curie temperature and loss of alignment in ordinary materials, the magnetic dipole moments of individual atoms produce magnetic fields that cancel one another, because each dipole points in a random direction, with the overall average being very near zero. Ferromagnetic materials below their Curie temperature, however, exhibit magnetic domains in which the atomic dipole moments spontaneously align locally, producing a macroscopic, non-zero magnetic field from the domain. These are the ordinary magnets with which we are all familiar. In paramagnetic materials, the magnetic dipole moments of individual atoms will partially align with an externally applied magnetic field. In diamagnetic materials, on the other hand, the magnetic dipole moments of individual atoms align oppositely to any externally applied magnetic field, even if it requires energy to do so. The study of the behavior of such spin models is a thriving area of research in condensed matter physics. For instance, the Ising model describes spins, dipoles, that have only two possible states, up and down, whereas in the Heisenberg model the spin vector is allowed to point in any direction. These models have many interesting properties, which have led to interesting results in the theory of phase transitions. Direction. Further information: angular momentum operator, spin projection, quantum number, and multiplicity. In classical mechanics, the angular momentum of a particle possesses not only a magnitude, how fast the body is rotating, but also a direction, either up or down on the axis of rotation of the particle. Quantum mechanical spin also contains information about direction, but in a more subtle form. Quantum mechanics states that the component of angular momentum for a spin s particle measured along any direction can only take on the values where c is the spin component along the ith axis, either x, y, or z. Si is the spin projection quantum number along the ith axis, and s is the principal spin quantum number, discussed in the previous section. Conventionally, the direction chosen is the z-axis, where sz is the spin component along the z-axis, sz is the spin projection quantum number along the z-axis. One can see that there are 2's plus 1 possible values of sz. The number 2's plus 1 is the multiplicity of the spin system. For example, there are only two possible values for a spin 1/2 particle, sz equals plus 1/2 and sz equals minus 1/2. These correspond to quantum states in which the spin component is pointing in the plus z or minus z directions respectively, and are often referred to as spin up and spin down. For a spin 3/2 particle, like a delta baryon, the possible values are plus 3/2, plus 1/2, minus 1/2, minus 3/2. Vector. A single point in space can spin continuously without becoming tangled. Notice that after a 360-degree rotation, the spiral flips between clockwise and counterclockwise orientations. It returns to its original configuration after spinning a full 720 degrees. For a given quantum state, one could think of a spin vector whose components are the expectation values of the spin components along each axis, i.e., this vector then would describe the direction in which the spin is pointing, corresponding to the classical concept of the axis of rotation. It turns out that the spin vector is not very useful in actual quantum mechanical calculations, because it cannot be measured directly. Sx, Sy, and Sz cannot possess simultaneous definite values, because of a quantum uncertainty relation between them. However, for statistically large collections of particles that have been placed in the same pure quantum state, such as through the use of a Stern-Gerlach apparatus, the spin vector does have a well-defined experimental meaning. It specifies the direction in ordinary space in which a subsequent detector must be oriented in order to achieve the maximum possible probability, 100%, of detecting every particle in the collection. For spin 1/2 particles, this probability drops off smoothly as the angle between the spin vector and the detector increases, until at an angle of 180 degrees, that is, for detectors oriented in the opposite direction to the spin vector, the expectation of detecting particles from the collection reaches a minimum of 0%. As a qualitative concept, the spin vector is often handy because it is easy to picture classically. For instance, quantum mechanical spin can exhibit phenomena analogous to classical gyroscopic effects. For example, one can exert a kind of torque on an electron by putting it in a magnetic field. The field acts upon the electron's intrinsic magnetic dipole moment. See the following section. The result is that the spin vector undergoes precession, just like a classical gyroscope. This phenomenon is known as electron spin resonance, ESR. The equivalent behavior of protons in atomic nuclei is used in nuclear magnetic resonance, NMR, spectroscopy and imaging. Mathematically, quantum mechanical spin states are described by vector-like objects known as spinors. There are subtle differences between the behavior of spinors and vectors under coordinate rotations. For example, rotating a spin 1/2 particle by 360 degrees does not bring it back to the same quantum state, but to the state with the opposite quantum phase. This is detectable, in principle, with interference experiments. To return the particle to its exact original state, one needs a 720 degrees rotation. The plate trick and Mobius strip give non-quantum analogies. A spin 0 particle can only have a single quantum state, even after torque is applied. Rotating a spin 2 particle 180 degrees can bring it back to the same quantum state, and a spin 4 particle should be rotated 90 degrees to bring it back to the same quantum state. The spin 2 particle can be analogous to a straight stick that looks the same even after it is rotated 180 degrees, and a spin 0 particle can be imagined as sphere, which looks the same after whatever angle it is turned through. Mathematical formulation operator edit. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. May 2021, learn how and when to remove this template message. Spin obeys commutation relations analogous to those of the orbital angular momentum, where epsilon jkl is the Levi-Civita symbol. It follows, as with angular momentum, that the eigenvectors of and, expressed as kets in the total S basis, are the spin-raising and lowering operators acting on these eigenvectors give where, but unlike orbital angular momentum, the eigenvectors are not spherical harmonics. They are not functions of theta and phi. There is also no reason to exclude half-integer values of S, and amidst all quantum mechanical particles possess an intrinsic spin S, though this value may be equal to 0. The projection of the spin S on any axis is quantized in units of the reduced Planck constant, such that the state function of the particle is, say, not, but, where can take only the values of the following discrete set. 1 distinguishes bosons, integer spin, and fermions, half-integer spin. The total angular momentum conserved in interaction processes is then the sum of the orbital angular momentum and the spin. Pauli matrices, edit, main article. Pauli matrices. The quantum mechanical operators associated with spin 1/2 observables are where in Cartesian components for the special case of spin 1/2 particles, sigma x, sigma y, and sigma z are the 3 Pauli matrices. Pauli Exclusion Principle for systems of n-identical particles. This is related to the Pauli Exclusion Principle, which states that its wave function must change upon interchanges of any 2 of the n particles, as thus, for bosons the prefactor, -1, 2s will reduce to +1, for fermions to -1. In quantum mechanics, all particles are either bosons or fermions. In some speculative relativistic quantum field theories, supersymmetric particles also exist, where linear combinations of bosonic and fermionic components appear. In 2 dimensions, the prefactor, -1, 2s can be replaced by any complex number of magnitude 1, such as in the ennian. The above permutation postulate for n-particle state functions has most important consequences in daily life, e.g. the periodic table of the chemical elements. Rotations. See also, symmetry in quantum mechanics. As described above, quantum mechanics states that components of angular momentum measured along any direction can only take a number of discrete values. The most convenient quantum mechanical description of particles' spin is therefore with a set of complex numbers corresponding to amplitudes of finding a given value of projection of its intrinsic angular momentum on a given axis. For instance, for a spin 1/2 particle, we would need 2 numbers, a plus or minus 1/2, giving amplitudes of finding it with projection of angular momentum equal to plus h/2 and minus h/2. Satisfying the requirement for a generic particle with spin s, we would need 2s plus 1 such parameters. Since these numbers depend on the choice of the axis, they transform into each other non-trivially when this axis is rotated. It is clear that the transformation law must be linear, so we can represent it by associating a matrix with each rotation, and the product of 2 transformation matrices corresponding to rotations A and B must be equal, up to phase, to the matrix representing rotation AB. Further, rotations preserve the quantum mechanical inner product, and so should our transformation matrices. Mathematically speaking, these matrices furnish a unitary projective representation of the rotation group SO, 3. Each such representation corresponds to a representation of the covering group of SO, 3, which is SU, 2. There is one n-dimensional irreducible representation of SU, 2, for each dimension, though this representation is n-dimensional real for odd n and n-dimensional complex for even n, hence of real dimension 2n. For a rotation by angle theta in the plane with normal vector where, and S is the vector of spin operators, parity, in tables of the spin quantum number S for nuclei or particles, the spin is often followed by a plus or minus. This refers to the parity with plus 4 even parity, wave function unchanged by spatial inversion, and minus 4 odd parity, wave function negated by spatial inversion. For example, see the isotopes of bismuth, in which the list of isotopes includes the column nuclear spin and parity. For by 209, the only stable isotope, the entry 9/2 means that the nuclear spin is 9/2 and the parity is odd. Applications. Spin has important theoretical implications and practical applications. Well-established direct applications of spin include nuclear magnetic resonance, NMR, spectroscopy in chemistry, electron spin resonance, ESR or EPR, spectroscopy in chemistry and physics, magnetic resonance imaging, MRI, in medicine, a type of applied NMR, which relies on proton spin density, giant magnetoresistive, GMR, drive head technology in modern hard disks. Electron spin plays an important role in magnetism, with applications for instance in computer memories. The manipulation of nuclear spin by radiofrequency waves, nuclear magnetic resonance, is important in chemical spectroscopy and medical imaging. Spin-orbit coupling leads to the fine structure of atomic spectra, which is used in atomic clocks and in the modern definition of the second. Precise measurements of the G-factor of the electron have played an important role in the development and verification of quantum electrodynamics. Photon spin is associated with the polarization of light, photon polarization. An emerging application of spin is as a binary information carrier in spin transistors. The original concept, proposed in 1990, is known as data-DOS spin transistor. Electronics based on spin transistors are referred to as spintronics. The manipulation of spin in dilute magnetic semiconductor materials, such as metal-doped ZNO or TiO2, imparts a further degree of freedom and has the potential to facilitate the fabrication of more efficient electronics. There are many indirect applications and manifestations of spin and the associated Pauli Exclusion Principle, starting with the periodic table of chemistry. History. Wolfgang Pauli lecturing spin was first discovered in the context of the emission spectrum of alkali metals. In 1924, Wolfgang Pauli introduced what he called a two-valuedness not describable classically associated with the electron in the outermost shell. This allowed him to formulate the Pauli Exclusion Principle, stating that no two electrons can have the same quantum state in the same quantum system. The physical interpretation of Pauli's degree of freedom was initially unknown. Ralph Kronig, one of Landes's assistants, suggested in early 1925 that it was produced by the self-rotation of the electron. When Pauli heard about the idea, he criticized it severely, noting that the electron's hypothetical surface would have to be moving faster than the speed of light in order for it to rotate quickly enough to produce the necessary angular momentum. This would violate the theory of relativity. Largely due to Pauli's criticism, Kronig decided not to publish his idea. In the autumn of 1925, the same thought came to Dutch physicists George Uhlenbeck and Samuel Goudsmit at Leiden University. Under the advice of Paul Ehrenfest, they published their results. It met a favorable response, especially after Llewellyn Thomas managed to resolve a factor of 2 discrepancy between experimental results and Uhlenbeck and Goudsmit's calculations, and Kronig's unpublished results. This discrepancy was due to the orientation of the electron's tangent frame, in addition to its position. Mathematically speaking, a fiber bundle description is needed. The tangent bundle effect is additive and relativistic, that is, it vanishes if c goes to infinity. It is 1/2 of the value obtained without regard for the tangent space orientation, but with opposite sign. Thus the combined effect differs from the latter by a factor 2, Thomas precession, known to Ludwig Silberstein in 1914. Despite his initial objections, Pauli formalized the theory of spin in 1927, using the modern theory of quantum mechanics invented by Schrödinger and Heisenberg. He pioneered the use of Pauli matrices as a representation of the spin operators and introduced a two-component spinor wave function. Uhlenbeck and Gaudsmit treated spin as arising from classical rotation, while Pauli emphasized that spin is non-classical and intrinsic property. Pauli's theory of spin was non-relativistic. However, in 1928, Paul Dirac published the Dirac equation, which described the relativistic electron. In the Dirac equation, a four-component spinor, known as a Dirac spinor, was used for the electron wave function. Relativistic spin explained gyromagnetic anomaly, which was, in retrospect, first observed by Samuel Jackson Barnett in 1914, see Einstein-de Haas effect. In 1940, Pauli proved the spin statistics theorem, which states that fermions have half-integer spin, and bosons have integer spin. In retrospect, the first direct experimental evidence of the electron spin was the Stern-Gerlach experiment of 1922. However, the correct explanation of this experiment was only given in 1927.